Good morning to everyone. It's a pleasure to be able to present the work here today. My name is Vinicius Kreischer. I am a software engineer and a researcher at LNCC, which stands for National Laboratory for Scientific Computing in Brazil. And I will present the work title, A Digital Twin System for Oil and Gas Industry, Use Case on Mooring Lines Integrity Monitoring. As some of you have probably noticed, there are a lot of authors in this work. It will become clear during the presentation why that's the case, okay? So this is the agenda of the presentation. I will start with a brief introduction, giving some contextual and motivation information about the work. So I'll present the architecture overview of our digital twin platform. We'll talk about machine learning models that we are using in our case. We'll talk about a use case using one of these machine learning models, which is called NEMO. And finally, we'll draw some conclusions and talk about future work. I would like to start by talking about Petrobras, which is the main sponsor of this work. Petrobras is a Brazilian petroleum corporation, okay? It's the largest oil and gas company in Latin America, and it has no expertise in deep and ultra deep water exploration production of oil and natural gas. It comes with a fleet of around 60 platforms, which you can see in the bottom two figures, some examples of these platforms. And with so many platforms, it's only natural that corrective maintenance and oil production stoppage are huge in this case, right? In the case of Petrobras, it's around 80 million annually. So one of the proposals of the company to tackle this issue is a significant investment in R&D projects. One important topic regarding research in Petrobras is that of mooring line systems, which one of the goals is to keep the floating unit in a stable position within an acceptable tolerance range. Once this floating environment factors as winds, waves, and currents, and operational challenges as corrosion and fatigue of this structure, okay? In this case, mooring lines integrity inspection is either impractical in the case of onboard staff, or is costly, especially if we consider the fleet number, which, as I said, is around 60, and these 60 platforms have around 1,000 mooring lines, okay? So digital twins present a promising approach for monitoring mooring line integrity. As a side note, these figures at the bottom represent the components of the mooring lines, okay? So there are steel chains, polyester ropes, and torpedo piles to fix the mooring lines at the bottom of the sea. Okay, so our proposal in this case is to develop a digital twin platform with some characteristics, but as mentioned during the start of the presentation, the high number of authors is due to the partnership that was formed for Petrobras with LNCC, which is the institution I belong to, as well as USP and PUC-Rio, which are renowned institutions in Brazil as well, okay? So the objectives of the DT platform are the integration of multiple specialized components. I will talk more about it later during the presentation. Support for entire machine learning lifecycle management of related artifacts. Seamless execution of machine learning tasks across diverse computational environments. Because, as we know, each service in a machine learning environment require different requirements, right? Reliable and robust machine learning models for each floating unit, and online prediction event detection. That's the final goal of the entire DT platform that we are developing, okay? I would like to highlight that it's an ongoing effort, promising results in real use case. We are already monitoring the multi-system line of the PC75 platform, which was represented in one of the figures in the first slide, okay? But it's being extended until the end of this year to 2 more platforms. Okay, so this slide demonstrates the general architecture of our digital twin platform. So on the left, we have the platform, the sensors on the platform, right, which send data to onboard server. This data is consumed by a stream data manager, which consumes this data, but also make this data available to Twinsy, which I will talk more about during the presentation. We have the domain data manager, okay, that has data related to, for example, the model of the platform, some characteristics of the model of the platform. We have the twin application, that's where the digital twin is managed. It's where the current state of the twin application can be observed. And we will also have at the bottom different execution environments, okay, which interface with Twinsy. So now I will talk about each one of these components, okay? Well, we have the twin application that, as I said, manages the digital representation of the real-world twin application, in our case, the platforms, actually the mirror lines of the platforms. This twin application is continuously updated, measured observations from sensor events. We have domain data manager, stream data manager that serve different purposes. The first one handles non-real-time data, such as characteristics of domain objects, the floating unit model, for example. And it provides a RESTful API for communication with other components of the platform. In the case of stream data manager, it manages stream data windows and processes serve capture data by sensors on the floating unit, for example, the position of the platform, okay? And it also provides RESTful API interface for integration. And finally, we have Twinsy, which is a component developed during the execution of the project. And its main idea is to manage machine learning lifecycle artifacts, in our case, data sets, learners, models, functions, and data flows, which I will explain later. And it also schedules and executes machine learning services in different computational environments, okay? Here we have the architecture of the Twinsy component that, as I said, serves the purpose of managing machine learning artifacts and executing services in different environments, okay? So we have here different roles for users. We have 2 interfaces for communication with the component called Twinsy Core, which is the component that receives requests from users for execution in different environments. And yeah, that's it. I'll talk about each one of these components, okay? So we have, as I said, different kind of users. We have administrators with manager user credentials and managed run environments. So a user with administration privilege can define execution environments. We have model developers which register data, pre-processing, post-processing scripts, and so on. Model developers also can train learners and produce models and tune parameters. And finally, we have enterprise systems, which interface with Twinsy to access its services, as well as the machine learning artifacts produced during the execution of tasks. Okay. Here we have a presentation of the 2 interfaces that Twinsy provides, which are a web UI and a RESTful API. In both cases, the functionalities provided are the same. Okay, the RESTful API is really useful in the case of enterprise systems that want to communicate with Twinsy. So here we have Twincy core that was presented in the general architecture, okay? So the idea, as I said, is that it receives requests for service execution from users and enterprise systems. And the main services provided by Twincy are the registration of datasets, learners, and models. Learners here are packages that contain the script for training models, as well as the dependencies that we need to use to train these models, okay? And the user also can configure and execute data flows. That is a concept that I'll present later, that it has been developed in Twincy. It also maintains a catalog for managing artifact metadata, and the final purpose of Twincy is also updates the Twin application with the results of the machine learning models, okay? Another important concept is the Twin's execution environments. So the idea is that it's an infrastructure for task scheduling. So we can have different computational systems as clusters, supercomputers, and cloud environments. Another component of a Twin's execution environment is a storage for managed artifacts, as well as MLflow libraries and server. We use MLflow in our case to isolate dependencies between different executions, okay? So one execution of a user does not interfere with the execution of another user regarding libraries used to perform this task, okay? Each environment runs a component called Twincy server, which is presented here at the left, which is basically a gRPC server that used to communicate with Twincy core. And Twincy execution environments send artifacts and metrics to an instance of a MLflow server, and these metrics or artifacts become available to Twincy core. Well, the concept of data flow is quite simple. It models a complete data process through a DAG of activities where vertices represent functions and edges represent produce-consumer relationship. There is an example which is covered by the window on the right, but it's quite simple. It's read data, fill missing values, normalize values, and train a model. Okay, it's a pretty simple example of a DAG of activities in the context of machine learning. Okay, so a user defines an abstract data flow. This can be performed by defining a JSON with a predefined language that we established, or through the web UI using drag and drop boxes. Okay. And this abstract data flow is mapped to different languages and engines. Currently, we support Kedro and Apache Spark, but we are working to support other languages and engines as well. And this mapping is sent to a Twin's execution environment. Okay. Now, I will talk briefly about the machine learning models that were developed in the context of this work. There are four. The first one is NeMo, which stands for Neural Motion Estimator. The idea is to detect Moorean line breaks by identifying changes concerning the expected motion of FPSO. FPSO stands for Floating Production and Storage of Loading Unit, which is a kind of platform. Okay. It predicts future platform movements based on 6 degrees of freedom: surge, sway, heave, roll, pitch, hang, and alert if the prediction motion differs from the sensed motion. So it basically predicts the future and compare with the actual readings, and if there is a significant difference, it emits an alert. Okay. In the case of NERO, which stands for Natural Frequency and Regression Estimator, the idea is to compare predicted resonant frequency with the observed ones. So it's quite similar to NeMo, but it uses another metric to predict if there was a problem with the Moorean lines. Okay, and we have two more models. The first one is NeuroSim, which stands for Neural Simulator. The idea is to simulate motion statistics of floating units based using neural networks, and the major use of NeuroSim is to aid movie system design by providing motion statistics for different metal-ocean conditions. The last machine learning model is SESL, which stands for Semantic Search in Offshore Engineering. It's pretty different from the first three. The idea is to retrieve, rank, and extract information for large document collections, and it acts as a communication interface, translating complex data in actionable insights. If you have any doubts about these machine learning models, some of the authors are here, okay? So you can question them about these models. Here we have an example of the use case of NEMO using Twinsy that I just presented. So I will not go into much detail, but the idea is that we have support for a training and an inference phase, okay? You can see that the training phase is not very usual, but even so, Twinsy is able to provide the capabilities needed to train the model, okay? And in the case of the inference data, you can see that we have a periodic process with 6 hours time windows that are sent to inference, to continuous inference in Twinsy. Twinsy performs pre-processing and regression using the different environments that I mentioned, and produce a result. On the right, you can see examples of the actual readings of the sensors regarding rho and UTMM, and the predicted values using the NEMO machine learning model. Okay. So to conclude, the digital platform that we're developing, it's an ongoing effort, okay? But it was capable to integrate different components to support the different the different stages of the DT platform that we needed. The proposed DT platform streamlines training, deployment, continuous inference using machine learning models, using Twinsy in our case. We were able to see that NEMO model was able to accurately predict Murray line failures, and also that the tests with NEMO model have yielded valuable insights to improve our platform, okay? And we were able to provide Petrobras with an online prediction and event detection platform. For future work, we want to integrate additional floating units and machine learning models that is being performed right now, as I said during the first slide. We want to leverage knowledge graphs for enhanced data integration. We also want to develop a rich interface for digital twin solution. And finally, we want to enable automatic decision-making, especially for model selection for inference. So we want to be able to predict the best version of a model to predict Murray line failures for each platform. We want to provide automatic model retraining using data and model drift aspects. And we also want to be able to select automatically the execution environment for a determined task execution, okay? So that's all. Thank you. And